to the first half of section 4.5, which is dimension. So today we want to make precise the definition of the dimension of a vector space. So we have a feeling for dimension, like lines are one-dimensional, but that feeling can sometimes break down, like, for example, what is the dimension of a fractile? So don't worry, we won't be finding dimensions of fractiles today, just vector spaces. So here's the definition. If V, which is a vector space, is spanned by a finite set, then the dimension of the vector space is the number of vectors in any basis of V. Now, an important fact down here is that if a vector space V has a basis of n vectors, then every other basis also has n vectors. So that means that this definition is well defined. You can use any basis you want, and the dimension will be the number of vectors in that basis. By definition, the dimension of the zero vector space is 0. And for infinite dimensional vector spaces, it's possible that V, the vector space, is not spanned by a finite set, in which case we say V is infinite dimensional. So here are some examples of dimensions of vector spaces that we've been working with so far. The dimension of Rn is n. And the standard basis, you could use any basis, but the standard basis that we know is E1 through En. That's n vectors. Pn, that's the space of polynomials of degree less than or equal to n, has dimension n plus 1. Standard basis is 1t squared, up to t to the n. That's n plus 1 vectors. The space of 2 by 2 matrices has dimension 4. And I've got the standard basis listed there over to the side. And the dimension of P, which is the space of all polynomials of any degree, is infinity. And that's because P is not spanned by a finite set. And there's a proof, I think I put one at the end, it's proof by contradiction. You assume that P is spanned by a finite set. You can always find a polynomial of degree, a higher degree than the highest one in your basis that wouldn't be in your basis. I didn't say that very well. The proof is by contradiction, but you can trust me on this one. The dimension of P is infinity. Okay, so what we want to do today is find the dimensions of subspaces. So here's some examples, and I've done some of the writing for us just to save time and so you don't have to sit there scribbling things down. The first one, find a basis for and the dimension of the subspace W of R4, and W is the space of vectors that have this form. So the first thing I did is I pulled apart a typical vector in W, looks like this, little w. I pulled it apart into the A vector, the B vector, the C vector, and the D vector. And then I pulled out the parameters, the A, the B, the C, and the D. That leaves me with 4 vectors, V1 through V4. W, by definition, is the span of those 4 vectors. So we've found spanning sets like that in previous sections. Now what we want to do is put those vectors into a matrix and find the dimension of the column space of that matrix. So if this should be a capital A. If A is the matrix with V1 through V4 in as columns, we want a basis for col A. And the number of vectors in that basis will be the dimension for col A, which is the dimension of W. So col A and W are the same space. Remember, col A is the space spanned by the columns of a matrix, and that's just how we've defined W. So I went through and did the matrix reduction for us. I put V1 through V4 into a matrix, and I reduced. Notice I only went to echelon form because I'm only looking for pivots. Okay, now recall from section 4.3, the way to find a basis for col A is to reduce A to echelon form B, and then we don't take the pivot columns from B, we take the columns from A that correspond to the pivot columns in B. So basis for call A is, I want columns 1, 2, and 4 from A. 1, 0, 0, 0. 1, 0, 1, negative 3. And finally, 0, 1, 1, 1. Okay, and the dimension of W is 3, because there's 3 vectors in there. Remember, call A is W, same thing. So a basis for W is this. Okay, let's do another one. Oh, notice W is spanned by 4 vectors, but we couldn't assume that those formed a basis because a basis has 2 requirements. Span, we have that, but they also have to be linearly independent. So it turns out that those 4 vectors were not linearly independent because actually a subset of 3 vectors spanned that same space that is spanned by this set of 4 vectors. Okay, another one. We want to find a basis for and the dimension of the subspace H of P2 spanned by these 3 polynomials. So that could be rather difficult working in the space of polynomials. So what we're going to do is use coordinate vectors and switch this over to a problem in R3. So the coordinate vector for the polynomial 1 is 1, 0, 0, because the coefficient of x and x squared, those are both 0. The coordinate vector for my next polynomial is 1, 2, negative 1. I'm just picking off the coefficients. And this one's negative 1, negative 2, 1. So if I let A be the matrix with these 3 columns, then what I want is a basis for call A. Because H is spanned by these 3 vectors. They may or may not be linearly independent. So if we find a basis for call A, then we'll find out. So what I did is I took A and I did 2 row reductions, got us down to echelon form, and I see pivot, pivot. So a basis for call A is, remember, I have to take the original vectors from A. So 1, 0, 1, 0, 0. That one didn't change. And the second one is 1, 2, negative 1. So the dimension of call A is 2. So therefore the dimension of H, which is the subspace of P2 spanned by those 3 polynomials, is 2. And then I can't leave my answer like this because I was asked to find a basis for H. H is a subset of P2, and what I've given is 2 vectors in R3. Now, there is an isomorphism between R3 and P2, but I want to give my answer as polynomials. So basis for H is, this corresponds to the polynomial 1. And the second vector corresponds to the polynomial 1 plus 2x minus x squared. So I've translated back to polynomial language. Okay, so you might want to pause right now and see how you're doing. Just try the next 2, and then come back and I'll do them. Okay, so let's start with number 4, because number 4 is very similar to what we've been doing. We want to find the dimension of the subspace H spanned by these 3 vectors. Now, we know that 3 vectors cannot be linearly independent in R2. So the dimension's either going to be 1 or 2, but it can't be 3. So what we want to do is we want a basis for call A with A equal to the matrix with these 3 columns. It's always good to write down what you're doing so people can understand what you're doing. Okay, and then if we reduce A to echelon form, we will get 1, -4, 2, 0, 0, multiply by -2 and add, -5, 2 pivots. So we're going to take the first and the third columns from A. Basis for call A, which is H, is 1, 2, and 2, -1. And the dimension of H is 2. We weren't actually asked to find a basis, but we had to do that in order to find the dimension. Okay, now this one, number 3, is a little bit different because there's an equation there. So it's the set of vectors in R3. So H is a subspace of R3. It's a set of vectors whose first coordinate minus the third is 0. So whenever I see an equation, I'm not thinking call A, I'm thinking null A. So in this case, H is actually equal to null A, where A is the matrix. The matrix of those, think of this as a linear system. This is 1, 0, -1. And when you find null A, you're looking at solutions to AX equals 0. So the augmented matrix would be, just augment this with the 0 column, 1, 0, -1, colon, 0. Okay, that's already in reduced echelon form. So we can just go ahead and write down the solution. Remember, we start at the bottom. In this case, there's 3 variables because there's 3 columns aside from the augmented. So X3 does not correspond to a pivot column. There's only one pivot column, so this is free. Call it T. X2 is free. We'll call it S. And X1 is T. So basis for null A is, I'm just going to skip, I could write this down, the solution down in parametric vector form and then pluck off the 2 vectors, but I think we've done this enough times just to skip right to the answer. The T vector will be 1, 0, 1, and the S vector will be 0, 1, 0. Order doesn't matter when you're putting things into a set. So there's a basis, and so the dimension of H is 2. Because here's a basis for H. Null A is actually the same as H. H is null A, the way I've defined A. Okay, so in terms of null A or call A, usually the tip-off is if you see equations over here, it's going to be a null A problem. But first you need to make sure those equations are set equal to 0 because null A is defined as the solution set of AX equals 0. All right, so now I'm going to preview some stuff from the next lecture, which is dimension of null A and dimension call A. If A is an M by N matrix, the dimension of null A is the number of blank variables in AX equals 0. Well, what would go there? Think about it. The way you get vectors in a basis for null A is each parameter in the solution to AX equals 0 gives you one vector, and you get one parameter for each free variable. So dimension null A is the number of free variables in AX equals 0. The dimension of call A, for each pivot column in the reduced matrix, you get a vector in the basis for call A. So dimension call A is the number of leading. Your book calls them basic. I call them leading variables in AX equals 0. It's the ones that aren't free. So the number of variables in AX equals 0 is the number of columns in the matrix A. That's n. So the theorem is dimension null A, which we'll call nullity next time, nullity, plus dimension call A, which we'll call rank next time, is equal to n. Rank plus nullity is n. Because together, you're either free or leading. So the free ones plus the leading variables has to equal the number of variables. So here's a really simple example. Find dimension null A and dimension call A. And we don't have to do any computation. Just look at A. 1, 2, 3, 4. There's 4 pivot columns. There's 1, 2, 3, 4, 5, 6 columns in all. So that corresponds to 6 variables in AX equals 0. There are 2 free variables. So dimension of null A is 2. And the dimension of call A is 4, because there are 4 leading variables. And sure enough, 2 plus 4 is 6, which is the number of variables. Some very heavy math there. 2 plus 4 is 6. Okay. Find a basis for null A, find bases for null A and call A, and verify the dimensions add up. So we'll do more of this next time, except we'll add row A onto the list. In this case, since we want a basis for null A, we have to reduce A not just to echelon form, because we're not just looking for pivots. If we only wanted a basis for call A, we could just go to echelon form and look for pivots. But we're going to have to go to reduced echelon form because we want to actually solve AX equals 0. So I augmented A with the 0 vector, and I reduced. It only took two steps, and this is what I got. And so if we want a basis for null A, we actually have to find the solution. So there's 4 variables. We'll start with x4. That's free. x3, the second line here reads x3 is 0. x2 is free. And x1 is negative 2s minus 4t. So we want a vector for the s's and a vector for the t's, and that will give us the basis for null A. All right, so our s vector will be negative 2, 1, 0, 0. And our t vector will be negative 4, 0, 0, 1. The dimension of null A is 2, because there's 2 vectors in the basis. Okay, for call A, this first part here is A, because this is A augmented with 0, and it's been reduced. Well, it's not A. This is the reduced form of A. I shouldn't say that. So this would be, okay, well, you know what I mean. If we take A and reduce it, the A part, the reduced A part is right here. And so I'm seeing pivot, pivot. That means I want the first and the third columns from the original matrix A. So basis for call A is 1, 2, and 3, 7. There's no reason to re-reduce A. Okay, so the dimension of call A is 2 also. And so verify the dimensions add up. Well, 2 plus 2 is 4, which is the number of columns in A. If we got dimension null A was 3 and the dimension call A was 2, we'd have a problem because 5 is more than the number of columns in A. It has to be equal to the number of columns in A when you add up. Okay, so we're almost done. Some basis theorems, and then I'm going to do true false, And then you got a couple practice problems for home that are super simple. Basis theorem 1. If V is a finite dimensional vector space and H is a subspace, then the dimension of H has to be less than or equal to the dimension of V. So that makes good sense, but I can give you a more concrete example, e.g. R3. This has dimension 3. R3 has dimension 3. Okay. The subspaces of R3 are lines going through the origin and planes going through the origin. Lines have dimension 1, which is less than 3. Planes have dimension 2, which is less than 3. The only three-dimensional subspace of R3 is R3. So you've got lines, planes, and then you've got R3. All right, second basis theorem. Let V be a vector space, and suppose you know the dimension. The dimension is P. Also suppose you have a set of P vectors in V. Then those vectors form a basis if either they span or they're linearly independent. Typically, we require both of those things. You have to verify span and linear independence. This theorem says if you know the dimension of the vector space, so suppose you're in R3 and you have 3 vectors that span, then you don't have to show they're linearly independent. You only have to show they span because you know the dimension of R3 is 3 and you have 3 vectors. Likewise, if you have 3 vectors in R3 that are linearly independent, they automatically span. So you only have to show 1. And you might be thinking, well, big deal. Well, actually, it is a big deal in real life. So if you're taking differential equations, is an example for DE students, the space of solutions to this second order homogeneous differential equation is 2. Now, suppose we find 2 solutions and we want to know if those span the solution space or if they form a basis. Well, it's easy to show those 2 solutions are linearly independent. We can take their Wronski and show it's not 0. It's harder to show they span the set of all solutions, but you get that for free. If you can show they're linearly independent, then they automatically span because you know the dimension of the vector space ahead of time. So that's an interesting theorem. All right, let's finish up with some true false. You might want to pause it, see if you can do these, and then pop back. All right, here we go. R2 is a 2-dimensional subspace of R3. We've seen this before. This is totally false. R2 is not even a subset of R3. You have to be a subset before you could possibly be a subspace, and it fails on that account. The number of free variables in AX equals 0 is the dimension of col A. That's false. It should be null A. Number of free variables is the dimension of null A. This one's a little tricky. A vector space is infinite dimensional if it is spanned by an infinite set. This is false. A vector space is infinite dimensional if it cannot be spanned by a finite set. It cannot be spanned by a finite set. That's different than saying it is spanned by an infinite set. And so to make that more clear, I'm going to give you a concrete example. R2, which we know is 2-dimensional, is spanned by the following set: 1, 0, and 0y, where y is any real number. So y could be 1, in which case you get the standard basis. Y could be 2, 3, 4, any number. That's infinitely many vectors. So R2 is spanned by this set of infinitely many vectors. It doesn't mean that R2 has infinite dimension. Okay, next one. The mapping x going to xb is called the coordinate mapping. And this mapping sends a vector to its coordinate vector where b is a basis for the vector space. That's true. We had one, I think, recently that was similar to this, but the arrow went backwards, so it was false. R3 and P2 are isomorphic. That's true. P2 is isomorphic to R. You add 1 to this number to get the R that it's isomorphic to. And the isomorphism is defined by taking a polynomial and sending it to its coordinate vector, just like we did in this example on page, I don't know what page it was, maybe page 2. We sent polynomials to their coordinate vectors in R3. Okay, back to our true false. If X is in V and B is a basis for V with n vectors, then the coordinate vector is in Rn. That's true, because remember what the coordinate vector is. You write X as a linear combination of the basis vectors. So let's call them B1 through Bn. You write X is C1 B1 plus ... Cn Bn. And then the coordinate vector is defined to be the C's, C1 ... Cn. So the number of C's you have is the number of basis vectors you have. And so if there are n of them, then yes, this vector is in Rn. Okay, if there's a set of 7 elements that spans V, then the dimension of V is 7. That's false, because you would also have to show that those 7 elements were linearly independent to say the dimension is 7, because you would need a basis. And finally, if V is 4-dimensional, then any set of 4 vectors that spans V is a basis for V. That's true by theorem 12 that we just talked about. If you know the dimension of your vector space, if you're given it's 4-dimensional, and you have 4 vectors that span, you get linear independence for free, so you have a basis. Okay, we'll finish up this section next time with the rank plus nullity theorem.